Welcome back to 3.1. Let's see if we can finish this up. So in our last part of our introduction to functions, we're going to talk about domain of a function, and we're also going to talk about combinations of functions. Let's talk about natural domain. Well, we've looked at a lot of functions before where they've actually given us explicitly the domain of the function. But we're going to look at a set of problems today where we're asked to find the domain. You might ask, well, how do normally they give it to me? How would I find it? That's where natural domain comes in. The natural domain of a function is the set of all real numbers you can plug into a function and get a real number back. You may notice this is basically the same definition we used for the domain of an expression back in R2, section R2. And yeah, it is basically the same thing. And the natural domain is really the set of all possible inputs. So when we look at examples, we're going to be looking at a function and seeing if we can figure out basically any real numbers that would be problems, because those we have to take out of the real numbers to build our domain set. So let's look. Here's a problem from the text. The instruction is find the domain. So let's look here. Looking at that, you have a fraction. The question you need to ask yourself is, okay, I'm plugging in real numbers for x, so anything on the real number line. There's positive numbers on the real number line, there are negative numbers on the real number line, zeros on the real number line. So is any of that going to make this function produce a non-real number? Well, really, there's only two kinds of non-real numbers we've looked at so far. One would be imaginary numbers, and imaginary numbers require roots, specifically even roots, to produce them, because we've seen the square root of a negative number is imaginary, so is like the fourth root or the sixth root. So there are no roots here, so that can't happen. How about undefined? Undefined is also not a real number. You may have forgotten by now. But we have an undefined number when we divide by 0. We'll actually have other conditions that'll get us undefined numbers later. But for right now, divide by 0. Well, we do have a fraction, so it is possible to divide by 0. When is that going to happen? To tell that, you've just got to look at the denominator. If the denominator is 0, we'll be dividing by 0. So when is x squared minus 4 equals 0? Because that's going to make it undefined. I guess another way you could say it is just set up this. This is probably a little bit simpler. This is what you need to be true for x to be in the domain. So let's solve it. X squared not equal 4. Square root both sides. Don't forget, you get a plus or minus. So x cannot equal plus or minus 2 if this is going to be defined. And you can see why. If you plug in 2, you get 0 on the bottom, undefined. If you plug in negative 2, you get 0 on the bottom. Some of my students would occasionally ask, well, what about 0? If I plug in 0, I'll get 0, which is fine. 0 is a real number. It's only when you divide by 0 that you get undefined. Undefined is not 0. Division by 0 is not the same thing as 0. So, how do we express our answer? Your homework will ask for generally two different notations. One might be set builder's notation. So that would just be this. All x such that x not equal plus or minus 2. And you can use the curly braces to indicate it's a set. The other way, you'd have to do interval notation. Interval notation, you have to figure out what your boundary points would be. So I cannot have negative 2. I cannot have positive 2. Well, then you have to break up the number line into intervals. Well, I can have everything to the left of negative 2, so that would be this interval. I can have anything in between negative 2 and positive 2, so that would be this interval. And I can have everything to the right of 2, so that would be this interval. So interval notation would be negative infinity to negative 2, Then we would have negative 2 to 2. And then we would have 2 to infinity. Oh, I forgot my union. There we go. Oops. There we go. And that would be the interval notation. It just depends on what the homework's asking for, which one you'll have to plug in. Sometimes it'll ask for interval notation, sometimes it'll ask for set builder's notation, and it'll actually probably go ahead and write this bit for you, and you'll just have to put in the condition. So that's a domain problem. Let's look at another one. In this one, we actually have a square root. We also have a division. So let's start with what we've already done. We know the bottom cannot be 0 in the domain. So I set that up. So if I solve for t, 3t would not equal 21. Divide by 3, divide by 3, t would not equal 7. All right then. That's one of the conditions, but it's not our only condition because we have an even root. Odd roots aren't really going to affect the domain, only even ones. So, if you remember, square roots produce imaginary numbers if their insides are negative. So, I need the inside of that root to not be negative. Well, if you're not negative, there's only two options. You're either positive or you're 0. So that's easy enough to set up. That's an inequality. Positive or 0 is greater than or equal to 0. Well, solve for t. T is greater than or equal to 4. So set builder's notation would be x such that x is, I'm not using x, I'm using t. T such that t is greater than or equal to 4 and t not equal 7. It's a little bit awkward. The interval notation isn't too bad. So we know we have to be greater than or equal to 4. But also, we cannot equal 7. So that means we have to cut out 7 like this. And we have two intervals, from here to here, 4 to 7, and from here to infinity, 7 to infinity. So that would be 4 with a square bracket, to 7 with a parentheses, union, 7 to infinity. And that's the interval notation. It's honestly probably a little bit shorter than the set builder's notation this time. That just depends on the set. If you have something like this, where you have a infinite condition here, like literally nothing to the left of 4, then often the interval notation will be shorter, whereas if you have to cut out just finite number of points like we did in the last one, we had to take out 2 and negative 2, a lot of times this one will be shorter. Just depends on what you've got. So that's finding domain. We'll get a little bit more practice in this section still, but we're going to move on to talk about combinations of functions. So these are new functions you can build from functions you already have. So if you have two functions f and g that have domain d and e, so d is the domain of f, e is the domain of g, you can build these combination functions. F plus g of x, this is function notation, this is the name of the function, this is the independent variable. F plus g of x is f of x plus g of x. You just add the formulas together and you get your new function. F minus g, you subtract them. Fg, this is the multiplication function. Sometimes you'll see the multiplication dot here as well. I really prefer this notation, but if you want to use the multiplication dot there, that's okay. And then f over g would be f of x over g of x. You could also have g over f, which would be g of x over f of x. This note right here, g of x not equal 0, that's just a side note saying This function doesn't exist if g of x is always 0, because it would always be undefined. You'd be dividing by 0. It also is an additional condition which affects the domain. All of these are functions themselves, and their domain is the intersection of the domains of f and g, except possibly for the division function. Because of that additional condition that the bottom not equal 0, that might actually take out another point or two. We'll see. Let's look at an example. So here's problem 73 from 3.1. We have two functions, f of x equal 1 plus 1 over x, and g of x equal 1 over x. And we're supposed to find f plus g of x, f minus g of x, fg, f over g, and g over f, and their domains. And then they just asked us to find a bunch of function values, which we can do that. We may actually skip that part since that's actually really quick, but I'll go ahead and do it this one. I think we have another one of these problems as well, so I may not do this part for that one. So let's do some work. All right, f plus g. That's easy enough. So we have 1 plus 1 over x plus 1 over x. We can combine like terms. That's 1 plus 2 over x. Might as well do this while we're here. F plus g of 3 equals 1 plus 2/3, which would be, let's see, 1 is 3/3, so 3/3 plus 2/3 would be 5/3. All right, f minus g of x equals 1 plus 1 over x minus 1 over x, which would just be 1. So that's easy. F minus g of 4 is 1. Because that's a constant function. It's always 1 no matter what you plug in. Then fg of x, that would be 1 plus 1 over x times 1 over x, which distribute through, you get 1 over x plus 1 over x squared. Yeah, I'm trying to decide whether I want to combine these into a single fraction or not. This is probably fine, but let's go ahead and at least look. This would probably be fine, but if I got common denominators, I'd multiply that by x over x, so I get x, x plus 1 over x squared. F over g. That's 1. Let's see, f is the 1. Yeah, f is the 1 plus 1 over x. 1 plus 1 over x over 1 over x. Divide by a fraction, you flip and multiply. So this is 1 plus 1 over x times x, which would just be x times 1 is x. X times 1 over x is 1. So this would be x plus 1. So f over g of 1 would just be 1 plus 1, which would be 2. G over f, this is actually a part I added into the problem, would be, oh, it's just the flip of this, isn't it? Yeah, it's the flip of f over g. So, since it's the reciprocal of f over g, it'll be 1 over x plus 1. But we'll go ahead and do it this way. 1 over x. Because you guys probably need the practice on doing complex fractions. So we've got a complex fraction here. The way we would simplify it is we would get common denominators, and then we would divide fractions. So like here, I need to get common denominators on the bottom. That will get me 1 over x plus 1 over x. Take the reciprocal, x over x plus 1, plus the multiplication sign. Cancel out the x's, we get 1 over x plus 1, as we were expecting. Alright, let's talk about domains. No roots in either f or g, so just have to worry about the division. 1 over x will just be undefined when x is 0. So the domain of f and g is everything except 0. So let me make a little table here. Domain, function, run out of room there. F will be everything except 0. So I'll do a quick interval notation. Negative infinity to 0, union, 0 to infinity. Is it the same thing? It is the same thing for g, because also can't be 0. So comma g. Well, that is a very simple intersection then, because they are literally the same set. Their intersection is also this. So that is also the domain of f plus g, f minus g, and fg by default. Then we look at our division functions. X plus 1, that's not going to be undefined for anything else because of division. So this is also f over g's. G over f, though, I cannot have negative 1 because that will make me undefined. So G over f has a slightly different domain. Let's see, I have to take out 1 as well. So if I took out 0, negative 1, not. And negative 1, that'll be 1, 2, 3 intervals. So negative infinity to negative 1 union, negative 1 to 0 union, 0 to infinity. And there we go. These would be all the domains. So everything except g over f had this domain. G over f had a slightly different one because of this being on the denominator. Let's do one more problem, and then I think we'll be finished with this section. So this is problem 76 from 3-1. I have a very similar g to last time, 2 over x instead of 1 over x, but f of x is this root. So if we look at f plus g, not as much simplification this time because of that root. Unless you're dealing with another root, you often can't do that much simplification. So square root x plus 1 plus 2 over x. There we go. F minus g of x would be square root of x plus 1 minus 2 over x. Can't really see my line there. It looks awful. Oh well. Fg square root x plus 1 times 2 over x. I guess I'll rewrite that a little nicer. 2 square root x plus 1 over x. And then f over g would be, let's see, square root x plus 1 over 2 over x. So you flip that and multiply, it'll basically just be x up there, 2 down there. So x square root x plus 1 over 2. And g over f. G over f would just be the flip of that. So 2 over x square root x plus 1. If you want to rationalize the denominator, you can. There's not a whole lot of point to do it in this case, but rationalize the denominator, you multiply both top and bottom by that square root, and you get 2 square root x plus 1 over x times x plus 1. All right, f and g. Let's talk about their domains. Function, domain. G is everything except 0. Union 0 to infinity. F is a little bit more complicated here. The inside needs to be greater than or equal to 0. So x is greater than or equal to negative 1. So it is just negative 1 to infinity. So if you look at those two sets, f is, here's -1, is -1 to infinity, and g is 0, is everything off this direction and everything off this direction. Well, the intersection, the set of numbers that would be in both sets, would be in between here, -1 and 0, and then 0 to infinity. So the intersection domain would be -infinity. No. -1 to 0. Yep. -1 to 0. Union 0 to infinity. That intersection domain is always the domain for f plus g, f minus g, and fg. If we look at f over g, it really doesn't have any additional conditions. It's not really dividing by anything unfortunate. So f over g would also go here. G over f, though, if you look at this, this is undefined at 0, which we don't have 0 in our domain anyway, but it's also undefined at -1. So I can't have -1 in the domain. It is right now because of this square bracket. So for g over f, I need to take that square bracket off, put a parentheses there, and now we are good. So that would be the domain of g over f. Is a -1 to 0, exclusive on both ends, union with 0 to infinity. All right, that'll finish us up on 3.1. Next time, we'll take a look at 3.2, and we'll start looking at graphs of functions. See you then.